welcome back to our second segment. We're still talking conservation of charge as well as quantization of charge. As far as the two, concepts in, interaction of charges, we are using insulators. They come into contact, we separate them, and we want to predict. It could be in the form, of a positive and a negative, a positive and a neutral. We'll try and explore different, possibilities in as far as, the far-reaching implication of, the principle of conservation of charge. So we're still talking conservation of charge, which cannot be separated from the fact that charge is actually quantized, right? So meaning that when charge is quantized, we are saying that we want to determine the magnitude of charge. So that's the basic, idea. So we've got two oppositely charged. We've mentioned that these oppositely charged insulators, okay, one is positive and one is negative. And then the thin thread does not allow the charge to be transferred, outside. So the total charge is actually between these two oppositely charged polystyrene spheres. Now, in terms of prediction, we want to understand the science as to what exactly happens in terms of charge during that physical process. Right. Now, these two charged objects are attracted to each other. Okay. Let's call this one Q1 for argument's sake. Okay. And then let's call the negative one Q2, as in charge 1 and charge 2 respectively. So we want to understand what happens here. But remember, we know that opposite or unlike charges attract. Okay? Opposite or unlike charges exert a force of attraction on each other. Ne? They attract each other. Okay? So in other words, there is a force exerted by Q1 on Q2 towards Q1. And then there is a force exerted by Q1 on Q2 in the opposite direction. But what is essential here is that they tend to pull together. Remember, a force is a push or a pull. So actually, the force on Q1 is by Q2 towards Q2 because it's an attractive force. So we know that one thing for sure, because these are charged materials, they exert a force of attraction on each other. So there is attraction there between the two. Okay, it goes without saying. And then if we bring them together on contact, and then this contact is what we would refer to as a physical process. Okay? So this is a physical process. So during contact, remember, the Q2 is negatively charged, while Q1 is positively charged. Okay? So Q1 is positive. Now, there is a transfer of electrons between these two. Now, these electrons are moved from Q2 to Q1. Why? Because Q2 has excess electrons. Okay? Q2 has excess electrons. Okay? While Q1 has excess protons. Okay? Has excess protons, which explains why Q1 has got a positive charge, right? And Q2 has got negative charge. So the transfer is actually with respect to electrons, all right? Now, as they transfer this charge, the charge is shared equally. So if we go back again, we know that the other one is +4 microcoulombs, while the other one is -10 microcoulombs. So the net charge in this case, in this closed system, Q net is equals to Q1 plus Q2, right? So the net charge in this case becomes, because the other one is +4 and then -10, it means this is equals to -6 microcoulombs. So this is the total charge in this system. So before they were brought into contact and after they were brought into contact, the net charge must remain the same, all right? Okay, so if the net charge remains the same, after making contact, they've shared this excess charge equally. So after making contact or during that process of coming into contact, they actually share charge equally. Okay, charge is shared equally. Okay, let's highlight that because it's very important. So charge is shared equally. Now we're talking about excess electrons in this case. They are shared equally. Now, if you come to think of it, the new charge on Q1 is now -3 microcoulombs, while the new charge after contact on Q2 is also -3. So now these two materials have got are identically charged. They're identical in every sense of the word in terms of the quantity of charge that each one of them carries. But now there is because now they are equal in terms of charge, now they are identical, they are like charges. We know that like charges exert a force of what? Of repulsion on each other. Okay, like charges repel each other. Okay, so this is what is happening now, because both of them now are negatively charged. Okay, but again, to show you something again that is very important, Q net is still equals to Q1 plus Q2, which means it's -3 plus -3, okay, which is still -6 microcoulombs. So our net charge before and after contact has remained unchanged. Hence we talk the term conservation. All right, okay. Now, we also want to understand something, okay, which is very important, okay, in terms of the number of electrons that were transferred, right? So we know the principle of quantization of charge says Q is equals to number of electrons lost or gained, okay, multiplied by the elementary charge. And remember, the elementary charge is a constant. It's -1,6 multiplied by 10 exponent -19 coulombs, all right? So there was transfer of charge from Q2 to Q1, right? Now, the new charge in each one of them, which is identical or which is also equal, is -3 times 10 exponent -6 coulomb, okay? We've already carried out the conversion there, all right? So if we talk about the net charge, we're talking about the sum of the -3 microcoulombs for Q1 and Q2. So the number of electrons transferred, if we can make that in the subject, it's going to be the change in charge. Let's take, for example, Q1 divided by the elementary charge, okay? The change is final minus initial. The final charge for Q1 is -3 times 10 exponent -6, okay? Minus the initial charge of Q1, which was plus 4 microcoulombs, which is 4 times 10 exponent -6 coulombs, okay? We divide this by the elementary charge, which is negative. Why are we using negative? Because Q1 gained electrons. It became more negative. In other words, it became less positive. So which is -1,6 times 10 exponent -19, right? So we can actually get the number of electrons that were transferred between those two, right? So the number of electrons transferred, we can go back to our calculator, clear that, right? It's -3, okay, times 10 exponent -6 minus 4 times 10 exponent -6. We divide that by the elementary charge, which is negative, okay, because Q1 gained, times 10 exponent -19. So this will give us an indication of the number of electrons that were actually transferred, 4,375. 4,375 times 10 exponent 13, okay, 4,375 times 10 exponent 13 electrons. So if this is the number of electrons that were lost by Q2, this is actually the number of electrons that were gained by Q1, which is actually the number of electrons that were transferred, right? Okay, we're still looking at that. Now, we have got two oppositely charged. We're still talking about the same experiment, okay, which says to us, okay, the new charge on the spheres, we've managed to determine the new charge, and we've said that Q new is actually equals to Q net, okay, divided by 2. All right. So this is actually the new charge, which is based on the net, of which the net we agree that it's -6 microcoulombs, right, divided by 2, because charge is shared equally. This gives us -3 times 10 exponent -6 coulombs, which is like, in other words, -3 microcoulombs, right? This is the new charge each one of them will have after separation, right? Okay, now we've managed to do that, okay? Now, we've got a different scenario altogether, okay? Just to go once more over the steps that we took in terms of predicting what happens. So we've got two insulators, they carry whatever charge, be it like charges or opposite charges. If you bring them into contact, the net charge remains the same even before actually bringing them into contact, because that's what the principle of conservation of charge says, that the net charge must remain the same during a physical process. So the physical process involves bringing these two together and separating them. And while these two are in contact, charge will be equally distributed between the two insulators. As a result of that, we get new charge, which is the same for QA and QB, or Q1 and Q2. And then we are able to say whatever the number of electrons that were actually lost by the one that has got excess is equals to the number of electrons gained by that material that has got excess proton that is more positive, in other words, which is also equal to the number of electrons transferred. That's the main idea around this, right? And also, here we've got a different scenario. Now, these are like, already, let's call this one QA, all right? -6 nanocoulombs. Let's call this one QB, right? Now, already, these two are what you call like charges. Actually, the forces must actually be away from each other. They are repelling each other, okay? Not exactly attracting. So let's just correct that, okay? So there's a force, but these arrows, they're saying that we put them together so that they make contact. So these arrows are actually saying they must put them, they must come into contact. But we know before they make contact, they tend themselves to repel each other because these are like charges, right? So these are like charges. So the white arrows, they suggest that they are brought into contact, but before they are brought into contact, they're actually pushing each other away, all right? And then after separation, this is what happens, okay? Now, we have got a scenario whereby it's -4, -6 nanocoulombs and -2. So if that's the case, our Q net in this case is actually equal to -8 nanocoulombs, okay? So the new charge on each one of them, Q new is equals to Q net, which is the total, divided by 2. Then this gives us -8 nanocoulombs divided by 2, which gives us the -4 nanocoulombs that we see. So each one of them now carries a charge of -4 nanocoulombs. But still, the force of repulsion still exists because they are still, in this case, essentially like charges. Okay, we'll take the discussion further after the short break, just to try and interrogate as to how many electrons were lost, which one lost and which one is gaining, and how many electrons were effectively transferred between the two. So we shall take that discussion further after the short break. Let's take a breather for now.